In this video, we're going to talk about recursion in Python, or creating recursive functions. Okay. So a recursive function, I guess, is a function that calls itself. That's it. I mean, it's pretty straightforward. We've had functions that call other functions. Now they're going to call themselves. We do have to be cautious about this. We don't want a program that has what's called infinite recursion, that it just keeps calling itself over and over and over again. So we're going to have to figure out a way for it to eventually stop. Okay. So let's take an example of a function that can be expressed in a recursive fashion. Pretty straightforward. That's the example of a factorial. Okay. So in factorial, or in exclamation point, the definition is as follows. If n is equal to 0, then we return a 1. Okay. If n is greater than 0, then n factorial is equal to 1 times 2 times 3 times all the way up till n. Okay. Because of all this multiplication, you'll note that factorials get big really quickly. Okay. So in order to create a recursive function, we're going to have to design a recursive algorithm. Okay. The algorithm is just a step-by-step way of solving the problem. Okay. So in particular, if we can get where we can determine the factorial of n based on the factorial of n minus 1, we're well on the way to developing our recursive algorithm. Okay. So we can switch things around here. It doesn't have to start with 1. Mathematics or multiplication doesn't matter which order it's in. So we're able to go from n to 1, basically. So I can write 4 factorial as 4 times 3 times 2 times 1. And if you'll note, I can also write 3 factorial as 3 times 2 times 1. Okay. So looking above this, we can see that this is just 3 factorial. Okay. That's what we were doing before. So we're able to write 4 factorial as 4 times 3 factorial. Okay. In fact, more generally, we can write the factorial of n to be equal to n times the factorial of n minus 1 for any n greater than 0. Okay, so we can write 10 factorial as 10 times 9 factorial. Well, what's 9 factorial? It's 9 times 8 factorial, and so on. So when does this end? Okay, it ends when we can provide a direct answer. So we can't provide a direct answer for 10 factorial. We have to wait until we figure out what 9 factorial is, which waits on 8, and so forth. So when are we done? We're done when we get to this base case. If n is 0, then we just return 1. Okay, so that's it. That's all we have to do. Okay, so let's look how this plays out in code. So we have our main function here, where I'm just going to enter a number, okay, convert it to an integer. And again, I'm putting a note here. I probably should put it, if I was going to give this to anybody else, to remember that factorials get big quick, so keep the number small. Okay, you could put less than 25 here, whatever you want. Okay, so in the factorial program, okay, so this is a recursive program. Okay, it's going to have 2 parts. Okay, the first part is going to be what we call our base case. Okay, when we can just return. Okay, so we know if n is equal to 0, we can just return 1. We're done. No, nothing else needed, right? Okay. So if n is, else if, we'll connect them together here, if n is greater than 0, okay, so now we have to do something else. Now we have to do our recursive step. Okay, so this then is the recursive step. Okay, and to get closer to my answer, I'm going to return n times factorial of n minus 1. Okay, and that's it. recursive algorithms are deceptively short. Okay. So if we think about what's going on here, okay, in fact, I'm going to stop the share here. I'm going to go to the whiteboard. We get to have fun with whiteboards. I know that's your favorite thing to do. Okay. So the basic idea here, yeah, got to write in a toolbook. That's fine. Can I get a bit? There's okay. So the first time we call it, and yeah, it's really ugly. If we're doing, let's say, 5 factorial. Yes, I'm drawing with my mouse. Looks like a 4-year-old did it. Okay. So in this case, when I do that, it's going to be equal to 5 times the 4 factorial. Okay. Well, I have to stop because I don't know what 4 factorial is. I've made another function call there. So I'm going to get another little box here. Okay. That's going to be 4 factorial, which is 4 times 3 factorial. Yeah, these are fun. Okay. Well, what's 3 factorial? Okay. I'm going to stop everything and wait for that to create 3 times 2 factorial. Okay. We don't know what that is. So these are all waiting. Okay. Then we're going to get 2 factorial is equal to 2 times 1 factorial. Okay. What's 1 factorial? Okay. That's going to be 1 times 0 factorial. Okay. So now we get to here and say 0 factorial. Okay, I know that one. Okay. That's equal to 1. So I return a 1 to here. So I now know the answer to this. 1 times 1 is 1. I return a 1 to there. So that is equal to 1. So 2 times 1 is 2. So I return a 2 to here. 3 times 2 is 6. I return a 6 here. Okay. And then 6 times 4 is 24. I return a 24 there. Okay. And the answer then becomes whatever 25 or 24 times 5 is. Let me do this here. 24 times 5 is equal to 120. You see what I mean about it getting big quick. Okay. So when we get to this point, all these are pending. These are all pending little bits of memory. Okay. When this gets its answer, it's gone, returns. This returns a 1, it's gone. So one by one, they collapse back down to give us the answer of 120. Okay. And if you have a calculator that does it, you can get, you can verify that the answer is 120, and it is. Okay. So that's the basic idea here. Okay. So again, if we didn't have the base case, this would never, it would never end, right? It would keep going on and on and on. Okay. So now we can run this and see if it gives us the correct answer. And then we're going to print what the factorial is. Okay. So let's run this. See what crazy mistakes I've made, because goodness knows I could have. Oh, here's my mistake. I didn't ever call main. Now let's try it. Okay, enter a number. So let's go with 5 so we know the answer. Okay. We get 120. Good. That's good. Okay. Just to kind of show what's happening here, to get beneath the scenes a little bit, I'm going to go ahead. Every time this function is called, I'm going to print out that we're there. Okay. So I'm going to have a print statement here. I'm going to say factorial, need a quote there. Function called with n equals n. Okay. So now when we run this, we should see if we do a 5. Okay. Just exactly what I was saying. We start with, it's called with n equal 5, then n equal 4, then n equal 3, then n equal 2, then n equal 1. And when it gets to n equals 0, Okay, so it's been in this top part in the recursive step every time until it gets to 0. Once it gets to 0, then we're done. Okay, then we return that and we're fine. Okay, so we could further, if we wanted, we could say, well, we'd have to wait. No, that's gonna be complicated. So we could say what we're returning. Okay, but we don't know that yet. Okay, so that's the basic idea behind recursive functions. Okay, so recursive functions are often the quickest and easiest way to solve a problem. So that could be a good thing. Okay, the downside is, from the picture I drew, all of those are taking up extra memory, so they're not the most efficient things. Okay, so if we wanted to do this without recursion, how would we do it? Okay, and it would just be through a loop. Okay, so if we have a, and if we're going to call this fact instead of factorial, well, he's not already out, so let's do a factorial iterative. Well, let's call I factorial. So the I factorial for n, just to show what that does, okay, we're just going to have our f, okay, which we can initialize to 1, and then we can say for I in range n, okay, so if n's 5, it's going to go 5, 4, no, it's going to go 4, 3, 2, 1. Okay, so I have to, let's do n plus 1. That should give us the correct range. Okay, we make sure this is working, so let me print I. Okay, never hurts to test things out as you go, especially with counter loops. You want to make sure that they're working. Okay, if I run this, iterate number 5 does that. Yeah, I'm going the wrong way. Okay, so I gotta go backwards. That's going 0, 1, 2, 3, 4, 5. It's the correct numbers, but I've got to get it to count backwards. Okay, so the range, I could do it that way. I'm guessing a while loop is here. Okay, so let's say I is equal to n to start. Okay, I'm going to say while I is greater than 0, okay, say f is equal to f times I, then I equals I minus 1. Okay, then let's print f. Let's see if this works. Yeah, that worked. Okay, so this does the same thing in essence. Okay, so that's either one's fine, but this can be a little quicker, a little shorter, not quicker. It can be a little shorter, but it's denser, so it can be harder to do. But especially the next course you guys take will be C++ and then data structures. We get to some things in data structures that are a lot nicer when you can do recursion. So you want to make sure that you're okay with recursion. Okay. And then again, if I didn't have this recursive step, it would just keep going down the page. The book has an example of that. Okay. So make sure if you have any questions that you let me know.